In this video, we are going to talk about some applications of integration, so specifically average value and mass. Our goals are to define and compute the average value of a function and to calculate the mass of a straight wire when the density might change at different spots along the way. So in this video, we will introduce what the average value of a function is, and we'll do an example where we calculate it. So first, let's recall, what's the average? If I have just a list of numbers, let's say I have finitely many numbers, what's their average? Well, to get the average, I'm going to call the average y subscript AVE. You just add up all the numbers. So y1 plus y2 plus dot 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 plus yn. And then you divide by the number of numbers. So there's n of them. And that's how you get the average of a bunch of numbers. So, well, I want to be able to get the average value of a function. So to visualize this, I'm going to draw two pictures. So I'm going to draw a set of axes, and then I'll draw one more set of axes over here to the side. And then I'm going to draw a couple of graphs. So first I'll start off with a simpler graph. Let's just draw a straight line. So a straight line, and then I'll have some interval from A to B. And let's say that at the x value A, and at the y value of the function is 3. And then at the x value B, that the y value of the function is 7. So I'll draw this y-axis a little higher. And let me label that the y value there as 7. Okay, and then in this second picture, maybe it's not a straight line anymore. Maybe my graph is more of a curve like this. And again, I'll have some interval from A to B. Okay, and I'll just draw a line up where this first endpoint is and draw a line up where the second endpoint is. So I want to figure out where is the average y value of the function on this interval from A to B. What's that average y value along the way? Well, in the first picture, because it's a straight line, I expect the average y value to be exactly halfway. So that would be at 5. Okay, and that's just due to the symmetry of this picture. This point where the average occurs happens to be kind of halfway between the A and the B. But if the function is curving like this, that average may not be at the halfway point. It might be somewhere over to the side. So how can I get a visual sense of where it's going to be? So I'm going to go back to my first picture for this first. So at this average y value, and let me go ahead and call this FAVE. If I draw a horizontal line through that point, and then once I reach the edge points, let me draw lines down to make a rectangle. The area of that rectangle matches the area under the function. The area under the function on that interval from A to B. Right, because the function contains this extra area up here that's above the rectangle, but then it has kind of an equal part that is missing that's part of the rectangle, though, that the rectangle counts. And those balance out, so the area of the rectangle will equal the area of the function. Okay, so that is what I'm going to try to find in this graph as well. Can I find some spot along the way where when I draw a rectangle at that point, that its area matches that total area under the curve along the way? And that's going to be my average y value. So I don't know exactly where that's going to be, but perhaps it's, I don't know, somewhere here. Maybe this is where the average, let me draw this, I'll label this as F av. Because then what should happen is if I draw this horizontal line to make the top of my rectangle, and then when I draw the sides, I'm really hoping that the area of that rectangle will equal this, the area under the function's graph over that interval. So my picture is definitely not perfect, but visually that is what I'm looking for. That is what I'm looking for. Okay, so I want this average y value to satisfy this condition. So let's break down each side. So for the area of the rectangle, I need to do base times height. Base times height. So the base of the rectangle is just b minus a, the length of the interval. And the height of the rectangle is, well, whatever that average y value is. And that's equal to the area under the curve, which we can write with a definite integral from a to b of f of x dx. So now to get this average y value, we just divide b minus a over to the other side. So that gives us this definition for the average value, where that average value is 1 over b minus a, multiplying that definite integral from a to b of my function dx. So I'm going to highlight this. This is my formula for the average value of a function. But conceptually, visually, what the average value is it's a y value along the way, where if I draw a rectangle at that y value, that rectangle's area matches the total area under the function on that interval. Okay, so let's do an example where we use this. So the problem says a cup of coffee is brewed at an initial temperature of 95 degrees Celsius. Its temperature T in degrees Celsius, so capital T is the temperature, after lowercase t minutes of cooling is given by this function. So capital T of lowercase t equals 20 plus 75 e to the negative 0.02 lowercase t. Okay, so when you plug in a value for lowercase t, whatever this whole thing equals is the temperature. The question says, what is the average temperature of the coffee during the first half hour after it is brewed? Okay, so I am trying to find the average temperature. So temperature is capital T. All right, T av. So using my formula, I should have 1 over b minus a. That's the length of the interval, which in this case, the first half hour. The first half hour would be from when t equals 0 minutes to t equals 30 minutes. So that would be 30 minus 0. And then my integral will go from 0 to 30. And then inside the integral, I put whatever function I'm trying to find the average of. And that's this function for capital T. I'm trying to find the average temperature. So 20 plus 75 e to the negative 0.02 lowercase t dt. Okay, and now it's just a matter of me finding this integral. So I got that 1 over 30 in front. And now I'm ready to do this antiderivative. Antiderivative 20 is 20t. And then that 75 is just a constant multiplying this e function. So that 75 will stay there. Okay, and then what's the antiderivative of that e portion? Well, I know the derivative of this using chain rule will be e to this stuff times the derivative of the stuff. And the derivative of the exponent is going to pop out a negative 0.02 when I do the derivative of it. So I need to cancel that out when I'm doing the antiderivative. So to cancel it out, I'm going to need a 1 over negative 0.02 in front of my e to the negative 0.02t. Okay, let me write this closed parentheses a little better. Close that parentheses, and then close that bracket, and now I'm going to plug in the 0 and the 30. So why is this the correct antiderivative? Well, to check it, I have to ask myself, okay, if I did the derivative of this, am I going to get this function over here? And the answer is yeah, because when you do the derivative of this e portion, you'll get e to this stuff times the derivative of this stuff, the derivative of this exponent, which will pop out a negative 0.2, which will cancel out this 1 over negative 0.2. And that'll end up matching what I started with. All right, so now let us go ahead and plug in. So doing that, I get 1 over 30, bracket, 20 times 30 is 600. And then in front of that, if I multiply 75 by this fraction, I'll get minus 75 divided by 0.02 times e to the, if I plug in 30 into the exponent, I'll get negative 0.6. Awesome. Okay, and then now I'm going to go ahead and I plugged in 30 and everything. Let's plug in 0. So when I'm plugging in, this 1 over 30 is in front of the whole bracket, which means I'm just going to leave that factored out. And I'm just going to be plugging into the stuff that's inside of this bracket. So now I'm going to put a minus sign. I'm going to put a big old parentheses, close the bracket, and now in the parentheses, I'm going to write what I get if I plug 0 into this whole thing. That's in the bracket. So when I plug 0 in, 20 times 0 is 0. And then that multiplies minus 75 over 0.02 times e to the 0. But e to the 0 is just 1. Okay, so if I didn't have a calculator, I could just leave it like this. I just need the units, and this is units of temperature, which for the problem are in Celsius. So this would be like in degrees Celsius. And I could leave my answer like this. Of course, if I have a calculator and I want to know what this is, it turns out this is about 76.4 degrees, rounded to 1 decimal place. Okay, and that is the average temperature of this coffee over that first half hour. Okay, so that is how we can calculate the average value of a function using this formula.